Okay, so let's get started with today's lecture. So we are going to talk briefly today about model-based vision, and this is the most classical approach to high-level vision that started in the early days. When people started talking about doing object recognition using computer vision. And then after that, we'll move to face recognition, where we will start talking about shading models. Sometimes they're called appearance models because they also include, obviously, some shape information that all started in face recognition, and that's what we're going to cover first. And then we'll go back to general object categorization and object recognition to see how these methods have been extended in recent years for solving that other problem. Okay? And then after that, we'll talk about more advanced or high-level vision systems. All right, awesome. So as I said from the very beginning of this course, object recognition is obviously the most fundamental problem in computer vision, right? And by that, I don't mean to degrade any of the other topics, but this is what most people associate computer vision to, right? That's what I mean. That one of, if not the end goal of computer vision is to do recognition of something, right? A visual recognition of some specific something in the world. And object recognition, it's the simplest, most obvious task that we can solve, okay? All right, so remember, if we go back to our first lecture, we talked about the brain, right, the human brain. We have the eye bulb here that connects to some subcortical regions down here inside the brain, and then from here it goes to early visual cortex, V1, V2, and so on. And then from here, it goes to some mid-level areas or mid-level vision that are located around this area. And then in this very frontal temporal part of the lobe, frontal part of the temporal lobe, this is where it is believed, or was believed at least, to have the computations that solve the object recognition problem, right? So we're going from low-level vision here, right, to mid-level here, and now to high-level vision, right? And the original idea is that with low-level vision, you're able to process the image in a variety of ways that allows you then to extract some landmark points or features of interest. You can organize these features of interest somehow to then, in high-level vision, construct a model, right? And by this, we usually mean a 2D, 2.5D, or 3D model of the object, okay, that we're looking at, or this scene, or as we'll see later, we can talk about other tasks in computer vision, okay? So far, so good? All right, so that's the original model that, or approach rather, that people discussed in the most classical computer vision systems approach. Now, there are two concepts that need to be, or that require clarification to understand why this model is difficult to define. The very first one that is rarely mentioned is what's an object, right? So that seems like a silly question, but it's a complicated question, right? So what's an object? That's a very difficult question to answer. I think that we all know what an object is, but we would have difficulty describing what this is, right? So if I'm looking at a face, is the face an object? Or is it an eye an object? Or is the iris of the eye an object? Or the pigmentation of the iris an object, right? Or is the human body an object, including the face? So it depends what we mean, right? And that has to be in your problem definition, because depending on the task of your computer vision system, you will want to use specific algorithms to solve it, because they're better adapted, better suited to solve that specific problem. Okay? So you have to keep that in mind, very important. And then the other problem that you need to address is what type of object recognition I'm interested in. Okay, so once I have defined what is an object for me in my application, I'm interested in determining what type of object recognition I want to work with. So am I interested in shape, which are the methods that we have already seen in shape analysis? Shape can define an object, but shape may not be the sole determinant of an object, right? Am I interested in shading? Shading is, as you know from 5460, an equally important component of the object. Is it a combination of the two? Or is it, for example, motion? Is motion the most important feature that I'm interested in? So there are psychologists that have demonstrated this more eloquently, perhaps. Gunnar Johnson's had this experiment many years ago, decades ago, where he would put, back then it was light bulbs, we put light bulbs in the articulations of a human body, right? And then would film the motion of the lights in a dark room, and all you could see were the light bulbs moving, right? And he showed that you could identify who was, if you knew that person, you could identify who that person was. If you didn't know them, you could identify their gender. You could most likely identify approximately their age. You could identify a number of actions that people were doing, like maybe running, walking, picking up a box, falling, etc. Right? Just by looking at the motion of these lights, right, of these joints. Excuse me. So there are many ways to object recognition, not just one. The other one is context. Context is also key for recognition. For example, if I were to look at a white blob in the middle of a road, I have an image, there's a road, and I see a white blob right in the middle. Probably I'm just going to ignore that, right? This probably doesn't have any meaning to me. But if I see the same exact same white blob in an image that has a computer and a keyboard, and the white blob appears next to the keyboard, I will interpret this as a mouse, right? The computer mouse. Context is extremely important, right? It doesn't mean that that object has changed in shape or shading. It's exactly the same thing, but depending on which context it is located into, it will be interpreted as A, B, or C, right? Okay. So object recognition is also made difficult by a variety of problems. One of them, of course, is viewing angle, right? The orientation of the object with respect to the camera. That makes object recognition difficult. It's not the same to look at, say, a cell phone as a frontal view like this, or a side view like that, right? Or at an angle like this. So depending on which image you take of a three-dimensional object at the specific orientations with respect to a fixed camera, or you move the camera, then the object shape and shading changes, and that makes it really difficult because of this 3D to 2D mapping, right? Photometric effects are also make photometric effects rather make object recognition difficult because the illumination changes the shading, right? And we spend quite a bit of time in 5460 describing this, right? And for specific objects, like objects that have a Lombardian surface, and for which we can assume that we only have one light source at infinity, a point light source at infinity, and things like that, there are some solutions like the illumination cone and extensions of that that allow us to find the set of all images of that object under all possible illuminations, right? But these are very specific cases, but the general problem still remains, and it's a very difficult one. Then there are other problems, like the shape of the object can change, right? It is possible for an object like a face, for example, to deform, right? And when the shape deforms, that makes it really hard for recognition, doesn't it? Right? It's not the same to have a face that is extremely deformed at an extreme or that it's at rest, right? And obviously, not only that, but your face and my face don't have the exact same shape, do they? Right? They are slightly different. So we have to account for deformations that are within some realistic constraint of what your face looks like, my face looks like, right? This variation across identity, but then the variation across expression as well, right? And that doesn't occur only to shapes. So for example, this object right here, right? This is an object A, a type of projector, but if I deform it like this, still the same projector, right? And if I move it like this, still the same projector, even though the shape has been deformed, right? So we need to understand this. That makes object recognition difficult. Okay, good. So that brings me to one of the ways to solving all these problems that I just enumerated, which is to build a shape model. Usually it's a three-dimensional shape model that represents the object that I want to recognize, okay? That is a specific model. Now, I will not talk about 2.5D. 2.5D is actually probably sufficient for most object recognition, but I'll stick with 3D shape. Now, the reason 3D shape is important is because, obviously, if we are able to extract the 3D shape of my object from the image, then that object or that representation is invariant to scale, translation, and rotation, and illumination, right? The question is, can I extract that three-dimensional shape? And that's what makes model-based vision difficult. Not the matching task at high-level vision, in the high-level vision problem that we're going to describe here today, but rather, can you construct this 3D model, right? And that's a realm of low-level vision and mid-level vision that we discussed already, right? So I think that there was a question in our last lecture that with regard to this, right? How can we do these things if our low-level vision algorithms like SIFT, SURF, and etc. Are not good enough to give us very accurate results? I'll talk more about this when we start talking about face recognition, because there are ways to address this, but not in this model-based vision, right? This model-based vision assumes this structure that follows the classical design of computer vision that goes from low-level vision, right? So I have a set of algorithms here that fit that information in mid-level, and then that fit that information in high level, right? That's the structure of the classical model-based vision. Okay, these algorithms are usually known, the model-based vision, that extract, so the idea is extract some landmarks, organize them in some useful way, and then create a 3D model, right, of the object. Okay. So these algorithms are usually known as hypothesis-based. Or also hypothesis and test. Hypothesis-based because you can make, once you have a three-dimensional model, you can make hypotheses on what you observe in the world, or given an observation in the world, you can make hypotheses on what this 2D image represents in 3D, right? And it is just logical that this was one of the first methods, if not the first method, to be developed in computer vision, because this is how this is how classical science works, right? The classical scientific method of design is to make a hypothesis on a problem, right? I have a scientific problem I want to solve. I make a hypothesis, and then I design some experiments that will test whether my hypothesis is true or false, right? Holds or doesn't hold. That's how science has always worked. And it just makes sense that the first thought scientists had when they wanted to build computer vision systems for the first time was to think like a scientist and say, I'm going to make a hypothesis and I'm going to test that hypothesis. So it just makes a lot of sense. Okay. The methods that were proposed within that framework fall within or have rather three main characteristics. That's A. First, we hypothesize a correspondence, meaning point correspondences or landmark correspondences between a collection of image features and a collection of object features that are present in our model, right? And this is our hypothesis. So we hypothesize a number of point correspondences between image features, or let's say image and object features, right? How about that? Object or model, if you prefer. Okay, so that's one way to do it. One first good characteristic. B, another characteristic of methods that use model-based is to use back projection. And what that means is that we use whatever current hypothesis that we have to generate a rendering of the object using a camera model, right? So we take one of the camera models that we have learned, affine, projective, doesn't matter, right? Whatever we're working with, and given a 3D model and a hypothesis of what I have in the image, I back project that 3D model onto the 2D image, right? And then I see whether there is a match, right? And I can make many hypotheses until I find the correct one, which takes me to step C, or characteristic 3, which is matching. And matching is the step where or the characteristic where I compare the back projection that I have made onto the image with the elements or the pixels of the image themselves. Okay, using some appropriate metric. Now, that means that for this to follow this number of steps, we need a hypothesis space, okay? And to better define the hypothesis space, let's assume that we have M features and capital N objects, okay? Actually, no, sorry. Image features and object features. My bad. And L is the number of objects. Okay. Right? So M, image features, that means the features that I extract from the image, right? They can be, for example, unions at multiple scales using a space scale theory, right? Okay. And object features, this is what's defined in our model, right? My objects are defined by N features, okay? By the unions, again. And L, the number of different objects that I have, right? The number of different object models that I have in my data set. Now, if we allow, okay, this is a question for you. If I allow all possible feature-to-feature correspondence from model to image, right? The total number, what would be the total number or the order of the total number of possible point correspondences? So the total number of possible point correspondences will be of the order of, anyone? So I have M image features, and I have to check these M features onto or in combination with the N feature models. How many possibilities are there? M so M for each M, I can check every single N, right? So it would be M to the N, right? And because I have L objects, it'll be times L, right? So obviously, the complexity of such an idea is absurd, right? Unless I have two objects and two features, in which case it's computable. If I have 1,000 objects and I have 1,000 unions in my image, then that becomes computationally expensive, right? Intractable. Okay. So this is just too large in general, obviously. Now, to limit the size of the hypothesis space, we can add geometrical constraints, right? So for example, we can restrict the search to Euclidean, or as you know, rigid transformations, right? So the m and n points are not necessarily random points, right? I can translate these points, I can scale them, I can rotate them, but I cannot break them, right? So if I only have rigid transformations, if the objects are rigid, obviously, in my image, then I can limit that. Okay. One method would be, for example, using post-consistency with an affine camera. So let's see how we could do that. So to do this, first, number one, we would select a small number of points, say a small m, right, from our model. Then number two, we make a hypothesis on the possible point correspondences. Make a hypothesis. And number three, use the camera model to see if they are consistent with the rest of the image points. Okay. So let's see with the m minus m points, right? So if I assume that I have an affine camera, then that means that I have my capital Pj's, remember, in three-dimensional space. Therefore, this is my model times A, which is the projection, the affine transformation, times pi equals a small p I. Okay. Now Pj here is going to be capital Pj is going to be in homogeneous coordinates, so it's 4 dimensions. Small pi is going to be 3 dimensions, right? Capital pi, it's a simple projection that defines my affinity, and therefore pi is where pi should be equal 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, right? Classical pi that we have seen. And then A can be just any transformation, right? So A11, A12, or actually in my notes I have 0, 0, 0, 1, 0, 2, 0, 3, A1, 0, 1, 1, 1, 2, 1, 3, and 2, 0, 2, 1, 2, 2, 2, 3, 0, 0, 0, 1. Okay. And that means that if I define this capital Pj as the vector, let's call it Pi0, Pi1, or Pj rather, and Pj3, 2, and 1, and the small pi, it's equal to I0, Pi1, and 1, right? Then if I follow these equations, Pi0 is equal to A00 capital Pj0 plus A01 Pj1 plus A02 J2 plus A03. And PI1, small pi1, is A10 capital PJ0 plus A11 PJ1 plus A12 PJ2 plus A13, right? And this is an equation that we actually saw in 5460, right? And one of, probably you saw it in one of the homeworks, if I'm not mistaken. So in this system of equations, we have 8 unknowns, if I'm not mistaken. Am I right? So let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So 8 unknowns, right? Yes. And which means that this can be solved with 4 or more point correspondences, because every point correspondence gives us 2 equations, right? So I need 4 or more points. And so what I can do is I can take 4 points from the model, right? 4 or features, right? Rather, 4 features from the 3D model, 4 features from the 2D image, make these point correspondences. That will give me a hypothesis, which are the A00, A01, right? The AIJs, right? And then that hypothesis then will construct this projection matrix, right? Now, once I have this projection matrix, I can predict, right, where all the other points of my model will be in the image according to that hypothesized point correspondences, right? And then if that matching is verified, then that means that that projection was correct, and therefore that our hypothesis was correct, right? And if that matching is incorrect, that means that our hypothesis failed, right? So that's a classical way of solving this problem. Another similar way to do that is by using coplanar points. You could use coplanar points to solve the same problem. So let's see this here very quickly. For if we use coplanar points, then I have pi0, pi1, the small p1 is equal to pi a capital pi0, pi1, actually 0, 1, right? Because they are coplanar, right? 0, 1, am I right? Because they are coplanar. And that means that I can write pi0, pi1, 1 is equal to a00, a01, a03, a10, a11, a13, 0, 0, 1, capital pi0, pi1, 1. And this means that views of a set of coplanar points in an affine camera are generated by affine transformations, right? This is a planar affine transformation. So if you select 3 points, or 3, let's say, model points, let's call them capital P0, capital P1, capital P2, right? My 3 points. Then any other point, capital P, can be written as is given by a linear combination of these three, right? Right? Because these 3 points span three-dimensional space, right? I'm only considering affine space. So I'm going to have, remember from barycentric coordinates, and we discussed this in 5460, I'm going to select 1 as the origin, like P0, for example, right? And then I'm going to have P1 minus P0 define one of the coordinate systems, or one of the axes of the coordinate system, excuse me, P2 minus P0, the other one. And then I'm going to have a coefficient, let's say mu I1 and mu I0, and that's going to define my point capital Pi, right? And hence, a point Pi, an image point Pi, is going to be given by some matrix C times capital Pi. And that means that this is C times P0 plus mu I1 times P1 minus P0 plus mu I2 P2 minus P0, right? And then that's equal to 1 minus mu I1 minus mu I2 times C P0 plus mu I1 times C P1 plus mu I2 C P2. And I can rearrange this as 1 minus mu I1 mu I2. Now, what is C P0? If C is the projection, right? The projection from the 3D world to the image. This is the camera matrix, right? So what is P0 times C equal to? A small p0, so this is small p0. And how about this one? A small p1 and small p2. And that gives us small p0 plus mu I1, small p1 minus p0 plus mu I2, small p2 minus small p0, right? And that means that I can define, and this is a very important result, right? I can define any point, right? Since I can define any point here, since I can define any point capital P as a linear combination, right, of three-dimensional points, I can define any image point as a linear combination of 3 two-dimensional points, right, on the image, the corresponding points in the image. Now, this is super important because it means that these points are affine invariant, right? It doesn't matter whether I have a translation, a scale, a rotation, or any other affine transformation. These coefficients are going to be the same for 2D and for 3D, right? You see that? So here's what we can do. select 3 points from your three-dimensional model. Okay? You have a three-dimensional model, select 3 points of that model. Now, every other point on your model is given by this equation. True? You agree? Okay. Now, you can create a table with all possible values for mu ij's, okay, in your model. Each time a model generates a possible mu ij that exists in your object, you add a vote. Okay? You include that this mu ij occurs, right? Once, twice, what have you, in your model. And then you check the same in the image, right? You see how many times the image has these mu ij's as well, these invariant uij's, right? Affine invariants, right? And if you find enough mu ij's that correspond between the image and the model, then they must correspond to the same object, because the mu ij's are invariant to the affine transformation from 3D to 2D, right? That's defined here. See how this works? Now, these methods, small variations of these methods I've described here today, were some of the very first very successful algorithms in computer vision, high-level vision. And they were specifically used for, anyone wants to make a guess? What they were used for? Very successfully for many years. I doubt I know most of the systems no longer use that, but some of the systems are still maybe using that. Probably a decent percentage of the systems that still exist may still be using these algorithms. Can you guess what the application of this, the famous application of all these methods is? It has to be something very geometric and something that you've seen for many, many years. I mean, that exists since I was a student, if you can believe that. You didn't see them or they were not as common as they are now. Now they've become completely ubiquitous. You can find them everywhere. But back then, they were already available. No? You want to make a guess? License plates, car license plates. That were the first very successful computer vision systems to be broadly implemented in the world. Every garage started putting cameras at the entrance and the exit of the garage to make sure that the cars were not cheating in entering and exiting, and making sure that they exit, or to count the number of cars and who was entering, who was exiting at what time. Now they are everywhere, and they're using a variety of methods. But you guess that still many of them are still using the old technology, which is this. Because for problems like that, these algorithms work really well. So why would we change them, right? No? OK, that brings me to a more sophisticated version of all this, which is recognition by linear combination of models. And by the way, I want to say these few algorithm ideas that I have described or derived thus far, plus especially the one that we're going to describe next, okay, show that if you could solve the low-level and mid-level problems that we have covered already, object recognition would be almost trivial, okay? The problem is, can you actually solve the mid-level and low-level vision problems, right? That's a real issue here. But let's see how we can do recognition by linear combination of models. And we're going to do this in 3D, obviously, 3D models. And that's just an extension of what we have seen. Very powerful algorithm. And as always, you have the paper in Canvas. So what we're going to do, we are trying to represent capital P, my three-dimensional point capital P, as a linear combination of 2D images, or the points in 2D images. Okay. Now, to do that, we're going to start with a very simple case. We're going to consider P1 and P2 two images of an object, let's say an object O. So maybe an object, it's this box. This is a three-dimensional box, looks like this. Okay. And maybe I can do this, clarify, right? So three-dimensional box. And so this is object O. And I'm going to take two pictures, P1 and P2 are two-dimensional images of that object. Okay. So P1 corresponds to that image, that frontal image that you see here. So I take a picture of this three-dimensional object. And then for P2, what I'm going to do, I'm going to rotate the object about the y-axis, right? So if this is the y-axis, I'm going to rotate the object as, say, alpha degrees, right? About that axis, and that is going to give me P2, right? So this would be frontal view as given, and this after alpha degree rotation. Okay. All right, so now as we have done here, let's consider what happens if I now rotate the object by omega degrees, right? So I rotate the object again, this time by omega. And that means that I'm going to obtain an image P hat, right? So maybe let's say that P1 is given by every point in that object, right? P1 is given an x1, x2. Actually, my bad, x1, y1, and P2 given by x2, y2. Then in that case, P hat is going to be given by x hat, y hat. And let's see what this is equal to. So in our case, the first case, x1 and x2, let me probably, for simplicity, say this is x and y, for simplicity of notation. So this is going to be x times the cosine of alpha plus z, the sine of alpha, comma y, right? Because y doesn't change because I'm rotating about y, right? Yeah. And here I'm going to have x times the cosine of theta plus z, the sine of theta, comma y. Okay? And this gives me, so this is capital P, by the way, capital P, right? So this is small p, small p. So this pi is in capital Pi, right? So these small points define the object, right? So given that equation, it follows that the third view, x hat is equal to ax1 plus bx2, and y hat is equal to y, where a is equal to the sine of alpha minus theta divided by the sine of alpha, and b is the sine of theta divided by the sine of alpha, right? And therefore, this equation gives us the solution for any other point in our object, right? In our image. Right? So given two images, I can then define any other possible image, basically. Yep? Now, what is most key about this result that I have derived there, this is the key concept to all this, is that the coefficients A and B, you see the coefficients A and B? They are exactly the same for all the points in that view. Right? It's amazing, isn't it? So you don't have to find different coefficients for every point in the view. Just have to find these two coefficients, and that gives you the coefficients for all the points in that view as a linear combination of the points in two other views. It's amazing. So let us now consider a more general case by assigning capital P1, P2, and P3 three images of my object O here that are now taken after an arbitrary rotation S. And let's say that S is in SO3, right? And let S be some rotation in three-dimensional space. Okay. Actually, let me do two. Why don't I do S and T? That way I can say P1 is the original view, P2 after applying S, and P3 after applying the rotation T. Okay. Now, if we have capital P hat as our fourth image, I want to describe that's obtained after applying a rotation U, right, in three-dimensional space. Now I want to see that I can describe capital P hat as a linear combination of P1, P2, P3, right, as I did before. And so S, remember, is going to be S1 transpose, S2 transpose, S3 transpose. It's the rotation matrix. Now, if I consider an affine space, an affine rotation, or an orthographic rotation to be more specific, right? One type of affine, then the third one doesn't matter, right? I only care about S1 and S2, right? So I can simplify these two, S1 and S2, and the same is true for T1, T2. And for this U. Okay. So this last row is not relevant to us. And for any, or for every P in our object O, I can write that, let's see, P1 is equal to x1, y1, which is equal to, it's equal to, okay, let me define. So P1 doesn't have any rotation. So let's say that the rotation matrix of P1, say R1, R2, R3, is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity matrix, which means no rotation, right? Yeah? So that way I can define this as R1 transpose P and R2 transpose P, right? This is P1. P2, x2, y2, which is equal to S1 transpose P, S2 transpose P. P3 is x3, y3 transpose is equal, let's say T. T1 P, T2 P, right? So far so good. And then I have my final one, any other new point, x hat, y hat. It has to be equal to U1 transpose P, U2 transpose P. Okay. So we'll assume for simplicity, obviously, that the sets R1, S1, T1 R and R2, S2, T2 are each linearly independent, right? So Ri, Si, Ti is a set of linearly independent vectors, right? So that they span the space, three-dimensional space, otherwise that wouldn't work. Which means that from these equations, I can define U1 as A R1 plus A 2S1 plus A3 T1, and U2 V1 R2 plus B2 S2 plus A3 T2, right? Yes, these two equations. So I'm now describing this U1 and U2 as linear combinations of R1, S1, and T1, and R2, S2, T2. And I can do that because they are linear independent. They span three-dimensional space, right? So every other vector can be represented as a linear combination of them. And then hence, I can write x hat as U1P, which is A1 R1 P plus A2 S2 P plus A3 T1 P, which is equal to A1 X1 plus A2 X2 plus A3 X3, right? Where I have taken this to represent, right, my known values, x1, x2, and x3. And I can do the same one. So this is for x hat. I can do the same for y hat, which in that case is going to be b1, y1 plus b2, y2 plus b3, y3, right? And these two equations, as we had before, show that I can write x hat and y hat as a linear combination of the other points, right? They're given by the corresponding known rotations. meaning that any new image, any image that I can take of any rotation of that three-dimensional object is given by a linear combination of these three original images that I've taken, right? You see how this works? See the idea? So that means that for each object, all I really need is three images, any rigid object rather. I need three images of that object, and then I can define any other view of that object, right? And any other translation of scale and rotation, because translation is just translating the origin, remember? Scaling is just the size of the object, so the normalized vector. And rotation, it's just given directly as a linear combination of these three images, right? So three two-dimensional images of a 3D object define every possible two-dimensional image of that object under every possible rotation, right? All right. Now that works for points, but not for smooth curves. So if I have a point or a line, that just works fine. But if I have a smooth curve, that doesn't work. So we need to solve one more problem, and we'll be completely done. So let's see how we can do that. So if I have smooth boundaries, or edges, or shapes, then I need to consider a rotation, right? Let alpha define the rotation about the x-axis. Beta, the rotation about the y-axis, and gamma, the rotation about the z-axis, okay? And that defines just three-dimensional space. Remember also from 5460 that we had this three-dimensional sphere, right? Where the coordinate system was located at the center of that sphere, the corresponding ijk or xyz, right? So in that case, could be xyz, right? Maybe actually to make it better, let's do it like this, xyz. And now here, when I define the rotation in this space from this point to that other point, right? I can describe that as first the rotation about the x-axis, then about the y, and then about the z, right? Okay. Now, remember that when we look from a camera, our coordinate system is located like this, pointing toward the image plane, right? And we have the x, the y, and the z pointing toward the image plane, right? So if I rotate about the z, the shape of the object doesn't change, right? So if I have a curve instead of a line, I have a curve. That curve is not going to change because I'm rotating on the plane, the image plane, right? But if I rotate about the x or y axis, so alpha and gamma here, no, alpha and beta, right? Then I am deforming the object, right? Okay. Oh, okay. In my notes, my bad. I'll correct this because my notes, I'm going to use my notes in. So in my notes, I have beta for z and gamma for y. for some reason. Well, I guess the reason is that's how it's in the paper that you have in Canvas. Now, as before, let P equal to xy be a two-dimensional contour point or part of an edge, and let P tilde x, y, z, rx, ry, t be the three-dimensional point where Rx, Ry define the curvature at that point P. Okay, so at that point P in my boundary of the or the edge of the object, right, or the shape of the object, there's a curvature, and then that Rx, Ry define that curvature. Okay. And to see that, imagine that you have a curve, a three-dimensional curve like this. And now you take a slice about the x-axis, right? And that gives you a radius for Rx that defines that curvature about the x slice that you have taken, right? According to the x-axis. So that would be Rx, and then you take it about the y, right, like this, and that would be Ry, right, that radius. So that defines a curve. Okay, and what else do we have? We know that if I have my point P tilde and I rotate that point according to R prime, I'm going to get, say, a small p prime, right? And this R prime can be defined as R11, R12, R13, R21, R22, R23. I'm just considering affine, so I'm just going to leave it at this. And then I need to multiply this by the rotations, the alpha, beta, and gamma that I have rotated. And that will correspond to negative the sine of theta, 1 minus the cosine of beta, and the sine of gamma, sine of alpha, 1 minus the cosine of beta, the sine of gamma, and I have negative the cosine of alpha, 1 minus the cosine of beta, the sine of gamma, and finally the cosine of alpha, 1 minus the cosine of beta, and the sine of gamma, right? And that will rotate x, y, z, rx, and ry, right? So now let's see how we can use this to define any point on an image or any image P hat of our object O from, now we're going to use 5 2D images, right? And these 5 2D images, let's call them P1, 2, 3, 4, and 5. Okay. And obviously, these images, we can say they are given after applying a rotation R1, R2, 3, 4, and 5. Yep. So I rotate by R1, usually the identity matrix for the first image, right? So I don't rotate, take a picture, rotate by R2, take another picture, R3, another picture, R4, another picture, R5, another picture. And that gives me the 5 pictures that I have. And now I can represent any new image P hat as a linear combination of these 5, right? And I use 5 because I have this result that I have derived above, right? So now every P hat is going to be given as by a linear combination of P1 through P5, right? So if we define any of these rotations, right? These rotations Ri are given by, they are affine, so we're going to say Ri transpose Si transpose. The first row Ri transpose, the second row Si transpose. Okay. So then I can write R hat. So I can write my rotation matrix R hat, which is the one that defines P hat, right, as R hat S hat, where R hat is given by the sum from 1 through 5 of AI Ri, and S hat is the sum from 1 to 5 of Pi Si, right? And since we have, following the same notation that we have derived here before, right? We have that X hat is equal to R hat times P tilde. Then we have that X hat is equal to the sum from 1 through 5 of AI times Ri times P tilde, which means that X hat is equal to the sum from 1 through 5 of AI Xi, and Yi it's equal to the sum from 1 through 5 of Pi Yi. And this is, of course, the same result that we have derived before for corners, other types of unions or lines, but now for smooth surfaces. And in that case, any point on a smooth surface can be represented as a linear combination of 5 views of that point, right? 5 two-dimensional views of that point. Any questions about this? So what these results show all in combination is that if we can solve the construction of the model, right, the three-dimensional model of the object, and we can extract the two-dimensional points correctly from the image, then all these things are they're given, right? The actual point correspondences are given by these equations. Now we have one final problem, which is the matching. Remember, we have to do the matching. And how are we going to do that? That's actually almost trivial for us now. So let's see it very quickly. So now what happens for matching? And By matching, I mean that I'm going to do a model to image alignment, right? I want to align the three-dimensional model to the two-dimensional image, right? And for this, what we're going to do, we're going to take a set of models, M1 through MK. I would say that this is the training or sample set of 2D images of P. Of O, right? And let P be the test image, right? And then I want to see if P can be approximately described as a sum from 1 through K of AI, AI, MI, right? So these are my simple images with K larger or equal than 5. Now, as we have seen already, a closed form solution can be obtained if we have 4 point correspondences, right? Then we obtain a closed form solution. But in general, I said 5 and I should say 4. But in general, I'm going to have more images, hopefully, right? I mean, at least I need 4 images. But what about if I have 10 images? I mean, one solution is I use 4 and I trash the other 6. But there's a better solution, right? Which is, yeah, say it. Don't be afraid. Right. We can use least squares, right? So use least squares to find a solution. So if we have capital X is the matrix of my X coordinates, of the aligned points with the model, right, as we have described here, and capital Y is the matrix of the Y coordinates that have been aligned to the model, then the least square solution is given by the pseudo inverse, right? So the least square solution for A is the pseudo inverse of X times PX, and B is Y pseudo inverse PY, where we have where I have used the notation that PX is equal to XA and PY is capital YB, right? Okay. And that's it. That's a least square solution, right, for A and B. Okay, any questions? All right, so I have one more thing that I wanted to talk about, another paper that I posted on a method that an extension of all this using deep neural networks that was used to break CAPTCHAs. CAPTCHAs are this text that are given to you when you open an account on a website or do something on a website. They give you a number of letters, right, that are rotated or deformed or with a weird background or with clutter, and you have to identify the letters, and they do that because they want to make sure that you're not a computer, right? So there is an extension of all this using deep neural networks from that extract low-level features, mid-level features, and then construct this three-dimensional model-based recognition that could break CAPTCHAs because it would recognize about 30 to 40% of the CAPTCHAs it was tested on, right? And if you have an algorithm that can break CAPTCHAs in about 10 to 20% of the time, CAPTCHAs are useless, right? Because the algorithm only needs to try 10 times if it's 10%, right, before getting in. So even if it works at 1%, it only needs to try 100 times, right? So anyways, this algorithm was really good. So completely out of time. I'll see if I can briefly describe this because that was supposed to be covered today in our next lecture, but I really want to start also talking about face recognition because otherwise I'm going to run out of time for all the topics that we still need to cover. All right, I'll see you Thursday.